Ange, and in this video we're gonna go through a way we can use calc1, right, to determine the formula of finding the volume of a given sphere. So let's think about a sphere this way. Okay, so we have this. It's a solid shape. So let's say we have this something like this, and then something like that. All right, good. So how do we find the volume of this sphere? All right. So since it is a three-dimensional shape, we can use the three-dimensional planes, right? X, Y, Z plane. Good. But here you're gonna see how we can use calc1, and that is just the XY plane in doing that, right? And of course, that is gonna be the integral. So let's see. Now, let's say we have the XY plane. So let me draw the y-axis like this. Okay, it's not straight. It's just anyhow. Okay, and then the x-axis. Good. So let me put it out here as y, and then x. Okay, good. Okay, so we notice that a sphere is if you want to think about this in two-dimensional, okay, that is a 2D plane, you just have to think about a plane shape like a circle. Good. So if we want to revolve a certain circle, let's say we have this particular quadrant. Okay, so let's say we cut the circle into four, and we have this particular quadrant like this, where from here to here is the radius of the circle, from here to here is the radius of not really a circle but a quadrant, right? Because we kind of partition a circle into four. Okay, we notice that if we revolve this circle about the y-axis, okay, we are going to form what we call a hemisphere, right? That is half of a sphere. So if we can get the volume of the hemisphere, you just double that and get the volume of the sphere, right? So what we'll be thinking about is the revolution of this curve about the y-axis. When we get that, then that would form what we call a hemisphere, and then from there, like I said earlier, you just find the volume of that and then double it and get the volume of this. Good. Okay, so what is this curve? If we know this curve, then that may be very, very helpful, isn't it? So let's think about this curve. Well, since I said a circle, you may think about the equation y equals to r squared minus x squared. That is, the equation of a circle is given as x squared, okay? The equation of a circle is x squared plus y squared equals to r squared. That is with center at 0. So maybe we just start off with 0 at the center, right? So if you have a circle about 0 at the center, this is the equation of the circle where the radius is r and then the center is 0. X squared plus y squared equals to r squared. So this right here is going to be such. But this is just 1/4 of the entire circle. So when we revolve this about the y-axis, we're going to get the semicircle, which by revolution will give us the hemisphere. Good. So maybe we can think about this as x being equal to the positive version of the square root of r squared minus y squared. That's just by making x the subject. Okay, so that is what we're going to call this curve. We're going to call the curve x, and that x is going to be given by this will make x the subject of formula. And in other words, that would be in a case where we've revolved this about the y-axis. Good. So we have the revolution. So when you revolve this curve like this, okay, it's more like revolving it about that. It forms a kind of a solid shape, right? But in the two-dimensional plane. Good. Okay, so that gives us what we call the hemisphere. So we can now notice that from here to here will be the same thing as from here to here, which is the r over here. Maybe this is the origin 0, from here to this r. Good. So to find out the volume of revolution, we need to get two things. Okay, the first is the cross-sectional area, and then the second will be the vertical height. So let's think about this. So we have this what I would call for now just a semicircle, but by revolution we mean a hemisphere. So maybe just take it down when we say hemisphere. So we think about it as a three-dimensional shape. So let me see how I can make that work. So we have, let's see, we have it this way. Yeah, that should help us out to showing us a hemisphere. Good. Okay, that's nice. So if we have that, good, that will be when we revolve this. So let's partition this into smaller cylinders to see what we get. Good. So if we partition this into smaller cylinders, notice that we're going to have something like this. Okay, maybe something like that, and so on and so forth. So that for a particular cylinder, it's going to look like this. So let's say we have, for a particular cylinder, we have something like this. Okay, good. Where this right here will be a partition in the y-axis, so I'm going to call it change in y. And then we will have what we call the area, the cross-sectional area of this cylinder. And by cross-sectional area of a cylinder, of course, for a right cylinder, of course, you know the area, okay, is going to be circular in shape. In other words, it's going to be pi r squared, where the r is the radius. So we know that the area here is pi r squared, that is the cross-sectional area, and then the vertical height for any piece will be changing y. Good. So to approximate this hemisphere, what we need to do is to take infinitely many pieces of such cylinders. In other words, this change in y will turn to dy. Good. And we can take the integral over the y variable from 0 to r, where r will be the radius of the circle we started with. Good. So that means that the volume of this can be given as, when we partition this into infinitely many, so let me just turn that into an integral, okay, as the vertical at the height. Now this is for each piece we have change in y, but y overall changes from 0 to r, where r will now be this, where r is the radius of this circle that we started with. All right, so we say the integral from let's put it down here, 0, okay, from 0 to r. Good. Of what? Well, we're going to multiply it by the area, so that will be by the area, which is given as pi r squared. Okay, then let me make it a little bit wider. Pi r squared times changing the y values, that which means which will get the y as the number of partitions get infinitely many. Good. So here will be the radius. But notice that for each of these pieces, all right, for each of these pieces, the radius changes. So the length from here to here for this particular piece is not the same thing as the length from here to here for this particular piece. Is not the same thing as the length from here to here for this piece, and so on and so forth. So it differs as we change our position on the sphere. Of course, the sphere is not a straight line, like maybe a straight line like this, like parallel to the y-axis, all right? So since that is the case, it means that the radius changes according as the y changes. Good. In other words, the radius is going to be this curve. So when this curve is here, that will be how long the radius will be from the origin, or from the x equals to 0 axis. Good. That means that here the radius will be given in this form. That will be the square root of r squared minus y squared. Okay, great. So we're going to square that square root and then evaluate this integral to see what we have. So we notice that pi is a constant. We can push that out. And then we have the integral from 0 up to r of, we square the square root to be left with just r squared minus r squared minus y squared. Good. Okay, so we put that over the y variable. So we integrate this real quick, of course, using the calc1, which I said, that's going to be pi. Good. Okay, so we notice that when we integrate the r squared over the y variable, we're going to get r squared y. Okay, and then that is to be evaluated from 0 to r. Good. Minus, we integrate this over y, that is y squared right here. That will give us 1 over 3 y cubed. Good. Using the inverse power rule. Okay, inverse power rule tells us that you add 1 to the power and then divide by the new power. Okay, that's what we get. I hope this is showing. Okay, so from here we would evaluate this. Sorry, we have to evaluate this from 0 to r. Okay, that's very nice. So let's see what we get from here. Good. So this becomes what? Well, when we substitute r in place of y here, this is going to be pi times, now that is r cubed, right? That is r to the third power minus 1/3 of, well, we put r here, that will be r to the third power. Good. Notice that when we substitute 0 for this term will become 0. When we substitute 0 for this term becomes 0 as well. So it's only the upper bound that we substitute. Good. Okay, great. So let's notice that when we subtract 1/3 r cubed from r to the third power, we're going to get 2/3, right? So that means we're going to have 2/3, 2 over 3 r to the third power times pi. Maybe let me put it out here as pi first, since pi is a known number. Good. Okay, so that's it, what we get here. And this, remember, this is a hemisphere, not yet the sphere, all right? So since it's half of the sphere, this right here is the volume. So let me put it out here, 2 pi over 3, how do you write it? Okay, let's say 2 over 3 pi, yeah, 2 over 3 pi r cubed. Good. So this is the what we call the volume of the sphere. So you say this is the volume of the hemisphere. Which is half of the sphere. So the volume of the sphere will become double, that is twice the volume of the hemisphere. So we're going to have twice of 2 over 3 pi r cubed. Good, because the hemisphere is half of the square. But notice that when we multiply 2 to 2 thirds, we're going to get 4 thirds, okay, pi r cubed. And of course, this is right here is what we know to be the formula of finding the volume of a sphere where the radius is r. Okay, that's very nice, isn't it? Okay, thanks for watching. Um, okay, so that is it, just by thinking about volume of revolution, all right, about the y-axis. Maybe you can also convert it to a problem about the x-axis. Maybe in that case, you put your hemisphere to be like this, maybe using the origin as a reference, just to make things easy. All right, thanks for watching. Please share this video with your friends, and I will see you in the next video.